Hi, everyone. This week, we're going to finish up our lecture on simple linear regression. When we left off last week, we had checked for our assumptions about our linear model to make sure that we could have confidence in the output. This week, we're going to interpret that data. If you recall last week from our cell output, we said that our linear model took the shape of y equals this intercept value plus this coefficient value connected to profile customers times x. The basic form of any linear regression model is that y, your dependent variable, is equal to beta sub naught, which is your y-intercept, plus beta sub 1, which is your regression coefficient, times x sub I, which is an individual data point from your independent variable. So let's look at the information that lets us know how well this equation actually predicts our data. The first thing we want to look at is our f value. This f value is a test for the slope, which determines whether or not our slope was significant. And by significant here, we really mean whether the slope is not 0. And here we see that the significance of f is less than 0.05. That means we have a significant slope. The null hypothesis for all linear regressions is that there is no linear relationship, that the slope is 0. The alternative hypothesis is that the slope is not 0. So this F test tells us that we can reject our null hypothesis of no slope, or reject our null hypothesis of a slope being equal to 0. Next, we look here at our R-square value. The R-square value tells us what percent of variance in the dependent variable is accounted for by the independent variable. Like all percents, this can range from 0 to 100%, which means that the R-square value can be anywhere between 0 and 1. What we read here tells us that roughly 85% of all of the variance in sales is accounted for by the profile of the customers. That's quite a bit. That means that only 15% of the behavior of the sales is unaccounted for in this one variable alone. Next week, we'll talk about adding additional independent variables to a regression model so that we can consider how more than one independent variable may work together to explain the variance in your dependent variable. Because we only have one independent variable in this model, we look to the R-square value for variance accounted for. Next week, when we have multiple independent variables, we'll look instead to the adjusted R. Now, I promised you that we'd talk a little bit this week about how related simple linear regression and correlation is. Recall that the symbol for correlation is lowercase r. Correlation and simple linear regression are really calculating the same R value. In fact, if I take the square root of our R-square value, this tells me what the correlation between profile customers and annual sales is. This means that correlation acts as a simple linear regression when the end goal is not to be able to plot and predict points. Because the end goal of regression is prediction, I do have a word of caution for you. It's not wise to use your regression equation to predict what new values of the dependent variable will be using independent variables values that go beyond the range you tested. Here, our lowest value is 2.2, and our highest value is 5.8. We can be very comfortable predicting annual sales based on profile customers that fall anywhere in that range and slightly outside of that range. However, it would be unwise to use this equation for a high-stakes prediction about annual sales using a customer profile of, say, 10, because we don't actually know how this equation might change once the range of independent variables goes beyond what we predicted. That relationship could change to be curvilinear. So because of that, we want to make sure that when we're making business decisions, we don't overestimate the power of our regression equation for predictions. And very quickly, I just want to take a quick look in our output from SPSS, where we see that once again, the data is in alignment. We reject the null hypothesis based on the F-test. We have 85% of variance in our dependent variable predicted to be accounted for by our independent variable by the R-squared. So we have perfect alignment here. As you work this week, please let me know if you have any questions about interpreting data from a simple linear regression.